Okay, let's start. Good morning, everyone. Thank you for joining my virtual workshop today. I'm currently conducting this virtual workshop from Japan, where it is midnight. What time zone are you joining from? Good morning, good afternoon, good evening. If you don't mind, please say hello in comment or any voice. I hope this workshop proves valuable for everyone. Now I will begin a workshop on how to use my optimization and design space exploration tool, Tunny. This workshop begins with lecture on optimization theory in the first half, followed by hands-on exercise using Tunny for practical optimization implementation in the second half. Before we start, there's something to confirm. First, this workshop focused on Tunny, a plugin that works on rhinoceroses, Grasshopper. While Tunny supports Rhino 7, it developed its primary targeting Rhino 8. You may encounter some bugs, so I recommend use Rhino 8 if possible. And Tunny partially uses GIS software. Please install this as well. It's the PC installable GIS software, not GitHub or GitLab. So make sure you don't confuse them. If you wish to participate in the hands-on session, please install these software. And Tunny can be installed through Rhinoceros as a package manager. And you can download Tunny V1 GitHub page. And license is required to use all features of Tunny. Participants who sign up will receive the following email. By joining the team using your Rhino account today, you will be guaranteed a license. If you have any issue, please let me know or let me send any message to the chat. And next, I will talk about a setup of Tunny. While Tunny offers numerous features, unlike other optimization components, it requires setup process within Grasshopper. Since the setup process takes some time, please complete this setup before starting hands-on session. First, open Grasshopper, then select Tunny from the top toolbar. So among the toolbar files, choose the topmost one. Once the file opens, double-click the tiny icon in the Grasshopper editor. This will start the installation of Tunny's required softwares. Okay, I will introduce myself before the Tunny lecture. Hi, my name is Hiroaki Natsume. Until 2019, I worked as a structural engineer at an architectural design firm in Japan. After that, I established my own firm and have been working on computational design focused on structure design. Within the work, I also began developing Tunny, which I'm introducing today. In addition to computational design, I participate in variable events, serve as a tutor, and engaging in computational design education in Japan and the surrounding regions. I also belong to the mechanical design company where I design various components of vehicle, heavy industry, home appliance, and more. Tunny is also used in mechanical design work, and I continue developing it while receiving feedback from a wide range of fields. Now let's begin the lecture on Tunny. I will introduce Tunny, a design space exploration tool that operates on Grasshopper, along with its background knowledge and software integration. Tunny's main feature is black box optimization. Before explaining the detail focused on Tunny, I will first talk about optimization. First, what is black box optimization? This is an optimization for progress where only the result is returned when the value is input. Since the operation is a black box and it is unclear what operations produce that value, it is called black box optimization. Optimization using Grasshopper is categorized as black box optimization because the outcome remains unknown until the calculation is performed within Grasshopper. Next, what is not black box optimization? For problems that can be clearly expressed as equations, such as this equation, the process and the resulting output can be calculated using a method other than black box optimization. Problems that can be clearly expressed as mathematical equations allow computers to automatically perform operations like differentiation and rapidly search for minimum value. In the case of Grasshopper optimization, since the outcome is uncertain until results appear, black box optimization methods well suited to this are often used. Optimization components such as Grasshopper in Galapagos, Forsey, Octopus, and Opossum are components that perform black box optimization. Someone waiting. Okay, I allow to these enter the Zoom. Okay, go to the next slide. Let's consider whether design is optimization problem. Generally, it is said that the optimization of design problem is a constrained optimization problem with multiple, often conflicting objectives. For example, this graph shows construction cost on a construction site on the vertical axis and the structure type on the horizontal axis. The cost varies depending on the type of chosen, whether to use reinforced concrete or steel, and whether to adapt a rigid frame structure or one utilizing bricks or walls. For example, let's say we are constructing an office in Japan. Since it's an office, we need a large open space. Therefore, it must be a rigid frame structure supported only by columns and beams. The structure type constraints have been determined. If there is no nearby factory where concrete material can be obtained, the only structure form available for this project is a steel rigid frame. This solves the problem of determining the structure type. In this example explanation, we determine the structure type very simple, but in the actual design process, it is decided through coordination with many stakeholders. Such actions are not well suited for optimization. It is something that designers themselves should do. So what is best suited for optimization? While computer optimization is excellent at performing detailed, repetitive calculations, it struggles with condition organizing as discussed earlier. However, within a fixed framework, it is skilled at fine-tuning and quantification, such as how many column and beam sections should we use, where should we place their resistant elements, how should the member be arranged. Let's tackle optimization with a clear understanding of what it does and doesn't do well. Change the subject. Is seeking a single optimal result always necessary in the first place? Have you ever wondered about things like these things? This requires statistical analysis, not optimization. Which grasshopper number slider value affect the cost? How does beam span affect structure safety? How does window opening size affect annual daylight gain? Tunny not only optimize but also support such statistical processing by broadly exploring the design space. This feature is also extremely useful for the example we will introduce. Let me walk you through the various optimization software available for design applications beyond Grasshopper. First, we have commercial optimization platforms that are primarily designed for mechanical engineering and industrial applications. These are enterprise-level solutions that come with a significant cost, but they offer exceptional versatility and comprehensive technical support. The major players in this space include Mode Frontier by Esteco, Heat by Siemens, Optimus by Noesis, and Eyesight by Dassault Systems. However, if you are working with a Grasshopper environment, there is a more accessible category of tools. Optimization plugin for Grasshopper. These are typically free and backed by strong community support, making them ideal for architects and designers who are already familiar with the Grasshopper workflow. Some popular options include Galapagos, Walsey, Opossum, and Octopus. But today, we will be focusing specifically on Tunny. As you can see from the various logos displayed in this slide, each of these tools has its own unique approach and strengths, but Tunny represents the latest development in making optimization more accessible and powerful for Grasshopper users. Now, let me share the story behind why I developed Tunny. As many of you know, genetic algorithms, or GA, are commonly used in architectural design optimization. However, they have a significant limitation. They require a large number of iterations to converge to an optimal solution. Before I started working on Tunny, I was using Walsey, which only supports the NSGA-II algorithm. While it is a solid tool, I ran into a major practical problem. Many of my optimization projects were taking over a week per run. Imagine waiting 7 days just to see if your design parameters were heading in the right direction. This timeline was simply impractical for most real-world project schedules. Architects and designers need faster results to iterate and meet deadline. So I want to find a faster converging optimization tool. The turning point came during an internal study session where we were exploring Bayesian optimization method. A colleague made an offhand comment. This doesn't seem too hard to build. That simple remark resonated with me. As someone who had been developing Grasshopper plugin for a while, I had always wanted to try my hand at implementing an optimization engine. That comment was exactly the push I needed. And just like that, development began. So Tunny was born out of a real need for speed and efficiency in the design optimization process. So here is a quick overview of Tunny development journey. I started development in early 2022 and released first version in April the same year. Since then, I've been releasing updates constantly, adding features like dashboard integration, constraint support, and notably, preferential Bayesian optimization support. But what made this journey truly special was the incredible support from the community. Your feedback, bug reports, and future requests have been invaluable in shaping Tiny into what it is today. And I'm thrilled to announce that after 2.5 years of development and refinement, version 1 is finally being released in August this year. This is a major milestone, and today Tiny is used by designer, engineer, researcher, and architects worldwide for their organizational workflow. Thank you all for being part of this journey. One of the most significant challenge and change in version 1 is the completely redesign of the user interface. As you can see from this screenshot, the interface have evolved dramatically from a plain text-based UI on the left to the modern icon-rich ribbon interface on the right. This transformation has dramatically improved feature discoverability and usability. In these earlier versions, users had to navigate through text menu to find features, which could be time-consuming and less intuitive. Now, with the new ribbon interface, all the major tools and the functions are visual, represented with clear icons and organized into logical groups, making it much easier to find what you need at glance. The redesign brings Tunny much closer to the polished, user-friendly experience you'd expect from commercial software, while maintaining the accessibility and flexibility of open source tools. The goal was to make powerful optimization capabilities more approachable for all users, whether you are a beginner or an advanced user. Now, let me walk you through the key features that make Tunny a powerful optimization tool for Grasshopper. Tunny is more than just a basic optimization tool. It bridges the gap between simple Grasshopper plugin and the enterprise-level platform, offering the best of both worlds. On the optimization side, Tunny supports a comprehensive range of algorithms, from advanced Bayesian methods like BOTPE and BOZP to evolutionary algorithms like NSGA-II and NSGA-III to simple sampling techniques like random and quasi-Monte Carlo. With auto selection, Tunny can even automatically choose the best algorithm for your problem. For visualization and analysis, Tunny provides powerful tools including history tracking, palette front plots, power coordinate view, and importance analysis. You can also use optional dashboard for web-based monitoring and TT Design Explorer for interactive design space exploration. This comprehensive feature set makes Tiny a complete design exploration platform for computational design, not just the optimization tool. One of Tiny's strengths is that it supports a significantly wider range of optimization algorithms than other Grasshopper plugins. Beyond the standard method, Tunny includes several advanced algorithms: autosampler for automatic algorithm selection, differential evolution for global optimization, MOEAD for specialized multi-objective problems, CMA-ES as a multi-objective variant of CMA-ES, CTPE for constant enhanced optimization, HEBO for fast converging Bayesian optimization, and INGO as an improved CMA-ES variant. We are also continuously expanding our algorithm library. Coming soon are gray roof optimization and whale optimization, both swarm-based algorithms inspired by animal hunting behaviors. This expansion is driven by user needs and the latest research development. We welcome feature requests and contribution from the community. So if there's a specific algorithm you'd like to see in Tunny, please let us know. Tunny uses Optional as its optimization engine, a leading hyperparameter optimization framework trusted by researchers and industry worldwide. Optional provides state-of-the-art algorithms that efficiently search large design space. It offers flexible search space, easy parallelization, and it's completely framework agnostic. Used across machine learning frameworks like PyTorch, TensorFlow, and scikit-learn. By leveraging Optional, Tiny brings this cutting-edge optimization technology directly to your parametric design workflow in Grasshopper. You are not just using any optimization tool, you are using the same advanced engine trusted by top researchers and the company around the world. The popularity and trust in Optional is clearly visual in its GitHub activity. With over 30,000 shares on GitHub, Optional has become one of the most widely adopted optimization frameworks. What's important here is the continuous growth. This shows that development is extremely active and the framework is constantly improving with new features and algorithms. You are not using outdated technology. You are using a framework that at the forefront of optimization research. This active development means Tiny benefit from ongoing improvements in optimization algorithms and methodologies, keeping your design optimization capability cutting edge. One of Tiny's most powerful features is it connected to Optional Hub, a platform maintained by Optional team where researchers and developers can publish their own optimization algorithms and methods. If you are familiar with Food for Rhino, Option Hub works in a similar way. It's essentially a repository or marketplace for optimization methods. Since Tunny uses Optional as its optimization engine, this integration means that any optimization method registered on Optional Hub can be used directly within Grasshopper through Tunny. This gives you access to a constantly growing library of cutting-edge optimization algorithms, from particle swarm optimization and the Bayesian method to specialized sampler for specific program type. As you can see from the screenshot, Option Hub features various optimization methods contributed by the research community, including visualization for palette front, robust Bayesian optimization, and multiple dimensional problem solver. This means tiny users benefit not just from the core algorithm I'm building, but from the collective innovation of the global optimization research community. It is extensively that make Tiny truly future-proof. As new optimization methods are developed and published, they become available to Tiny users. A key advantage of Tiny is its built-in result analysis capabilities. You can perform quick result checks directly within the Tiny user interface. No separate dashboard required. As you can see on the screen, Tiny provides comprehensive visualized tool. On the left, we have the optimization setting and parameter controls. In the center and right, you will see various visualization options, include scatter plot for the multi-objective analysis and the palette front plot that help you understand the trade-off between different objectives. These visualization features allow you to immediately understand your optimization results and make informed decisions about your design parameters, all within a single integrated environment. Tunny features Varose-style result output interface. A key advantage is the ability to import selections from optional dashboard or TT Design Explorer back into Tiny for output control. This creates a seamless workflow between different optimization tools, allowing you to leverage the strengths of each platform while keeping Tiny as your central hub. Tiny provides easy access to support resources directly from the Ribbon interface. You can access comprehensive documentation, FAQs, and AI-powered support with just one click. This integrated help system ensures you can quickly find the answer to your questions without leaving your workflow. And while not featured identical to the Windows version, Tiny also supports Mac OS. In fact, Tunny is one of the few Grasshopper plugins for Mac OS that supports both constraints and multi-objective optimization. An important difference is, while the Windows version requires a license for certain features, all features in the Mac OS version are available without a license. This cross-platform capability makes Tiny accessible to a wide range of users, regardless of their operating system preference. The Tunny uses color-coded components to provide clear visual feedback in your Grasshopper workflow. Each function has a distinct color, making it easy to identify the role of each component at a glance. This visual organization helps you quickly understand your optimization setup and troubleshoot your definition more efficiently. Tunny saves optimization results as a text file, separate from the Grasshopper document. By default, results are saved to a fish log file on your desktop. Once saved, you can view and explore your optimization results through the web-based dashboard, even without Grasshopper. This allows you to analyze the result and present to stakeholders anywhere, making your optimization insight accessible and shareable beyond the design environment. Detailed dashboard usage will be covered in the hands-on session. Tunny seamlessly export to Design Explorer, developed by Sonton Tomaselli, the organizer of this workshop. If you are already familiar with this industry standard analysis tool, you can continue using it to explore your tiny optimization results. This integration provides flexibility, allowing you to leverage the powerful visualization and analysis capabilities of Design Explorer within your existing workflow. So with so many features, it can be challenging to master everything Tiny offers. Our AI assistant let you ask questions about any feature in natural language, making it easy to get the help you need. Whether you are wondering about specific samples, optimization algorithm, or how to set up constraints, the AI support provides instant, context-aware guidance to help you work more efficiently. And this is the last slide of Tiny feature. Users have reported that Tiny may not function properly in these environments. I am aware of these issues and plan to address them in upcoming release. Okay, now let's explore the different sampling methods available in Tunny. Understanding these methods is crucial for effective optimization, as each sampler has unique characteristics suited for different types of problems. We will look at how different samplers explore the design space and when to use each one. Tunny offers an extensive collective of methods for optimization and analysis. On the sampling method side, you have access to various algorithms, including auto-selection for automatic sample selection, Bayesian optimization methods like BOTB and BOGP, evolutionary algorithms such as NSGA-II and III and MOEAD, and other advanced methods like CMA-ES and differential evolutions. Let me explain the key characteristic of each sampling method category. Auto-sampling, auto-selection provides automatic selection of high-performing algorithms based on your problem. Bayesian optimization methods like BOTP, BOZP, and HIBO achieve fast convergence by building surrogate model of your design space. Evolutionary algorithms, including NSGA-II and III, MOEAD, and DE, differential evolution, are well-established method. OC also includes NSGA-II, which, while slower to converge, provides reliable performance across a wide range of problems. Evolution strategies like CMA-ES and INGO are currently limited to single objective problems in Tunny, but excel at handling highly multimodal landscape with very fast convergence. And finally, random, Cauchy Monte Carlo, and brute force are sampling-only methods useful for exploring relationships between variables and objectives without optimization. Now, you might be thinking in two ways. So many options, perfect. I can always find the best algorithm for optimal performance. Or perhaps, wait, there are how many? This is overwhelming. I don't know where to start. Which one are you? Don't worry, I will help you understand when to use each method and guide you toward the right choice for your specific optimization challenges. You might have several questions. GA, like NSGA-II, is common in other Grasshopper plugins. Should I just stick with this one? Or can I always use TPE or auto sampling? Tunny's top recommendations. Or what is the point of non-optimization methods like random or QMC? Let's explore three key algorithms in Tunny, NSGA-II, TPE, and QMC. But first, Tunny version 1 introduces autosampler, which automatically selects the best algorithm for you. I recommend it to starting there. This slide introduces about GA. This is probably the most familiar algorithm to many users, inspired by biological evolution. It's widely available in other Grasshopper optimization tools like Galapagos, Walshy, and Octopus. Like natural evolution, results improve gradually over time. This method improves optimization result with each generation. Good traits are passed from parent to offspring. The process works in two key steps. First, crossover. Select high-performing individuals as parents and generate offspring that inherit their characteristic. This combines the best trait from successful solutions. Second, mutation. To maintain diversity, occasionally introduce random mutation. This helps explore new area of the design space and prevent getting stuck in local optima. This evolutionary approach is reliable and robust across a wide range of problems, making it a trusted choice for much objective optimization. And next one, this approach may be less familiar to many. SMBO stands for Sequential Model-Based Global Optimization. Think of it like creating a trend line or curve fit in Excel. The algorithm builds a surrogate model, which is an approximation function of your design space, then uses this model to efficiently guide the optimization process. This process works in stages. First, build a surrogate model based on samples from the design space. Then, with an accurate surrogate model, SLBO can find optimal solutions much faster than genetic algorithms by predicting which areas are most promising. Finally, perform strategic exploration of promising region identified by the surrogate model, continuously refining the approximation. This intelligent model-based approach makes Bayesian optimization particularly efficient for expensive evaluations, as it minimizes the number of actual design evaluation need. SLB will also include RBF opt from Opossum. Opossum is another Grasshopper optimization tool that uses this surrogate-based optimization approach. Finally, I introduce about QMC, quasi-Monte-Carlo. This is especially useful for machine learning and design space exploration, which we'll discuss later. QMC minimizes sampling bias through high uniform space convergence. You might ask, does not random sampling avoid bias too? The answer is, random sampling is only truly uniform with infinite samples. In practice, it creates clusters and gaps. QMC uses mathematical theory to distribute samples more evenly with fewer points. As you can see in the comparison, random sampling on the left shows noticeable clustering and empty space, like this area or this area. While QMC on the right demonstrates much more uniform distribution across the entire design space. This makes QMC particularly valuable when you need comprehensive coverage with a limited number of sampling. Both the vertical and the horizontal axis represent parameters. The color intensity indicates the trial number. Darker colors correspond to points sampled later. But honestly, if you are just getting started or want to optimize without worrying about all these details, the answer is very simple. Anyway, I want to optimize it. If yes, please use AutoSampler. The AutoSampler automatically selects the best algorithm for your problem, considering factors like the number of objectives, constraints, and trial budget. It takes the guesswork out of method selection, making it the perfect starting point for most users. You can always experiment it with specific algorithm later once you become more familiar with optimization. But AutoSampler gives you solid result right from the start. If you want to manually choose a method, Here is a practical guide based on your problem characteristic. The decision tree is simple. Start with number of objectives, then consider number of trials. For single objective problems, use HIVO for up to 300 trials, GP optional for up to 1,000 trials, or CMA-ES and INGO for up to 10,000 trials. For 2 or 3 objectives, use GP optional for up to 300 trials, TPE for up to 1,000 trials, and NSGA-II for up to 10,000 trials. For 3 or more objectives, use NSGA-III or MOEAD. When your problem includes constraints, the selection guide changes slightly. For single objective problem with constraint, use GP optional or CTPE. For 2 or 3 objectives with constraints, choose GP optional, TPE, or NSGA-II based on your trial budget. For 3 or more objectives with constraint, use NSGA-III. The key difference is that constraint handling requires algorithms that can efficiently navigate feasible region, which is why Bayesian methods like GP and constrained TPE variant are recommended for smaller trial budgets. When you are not optimizing, but simply exploring the design space, the decision is straightforward. If you need low discrepancy sampling, evenly distributed points across the space, use QMC, Quasi-Monte Carlo. If you don't need low discrepancy, ask yourself, do you need all results? If yes, use brute force to exhaustively evaluate every combination. If not, random sampling is sufficient. Okay, now let's look at some performance benchmark to see how these different algorithms compare in practice. Understanding the actual performance difference will help you make more informed decisions about which method to use for your specific projects. OC is one of the most widely used optimization tools in Grasshopper. Let's compare the result from each tool using their default settings. I will use the Oakley function as this test case. OC uses the following optimization configuration: NSGA-II and SBX, simulated binary crossover, and polynomial mutations. Force's default configuration focused on intensively searching promising region. This is called exploitation. In contrast, Tunny's default balance through exploration of the entire design space with exploitation of good solutions. Even with the same underlying genetic algorithm, these configuration differences lead to significantly different results. On the left, you can see Wolf's convergence is smooth and constant across all 3 lands. On the right, Tunny's results show much more diversity, exploring a wider range of the design space before converging to optimal solutions. When time settings are adjusted to match Wolf's configuration, both two achieve comparable results. The convergence patterns are now very similar, confirming that both two are working correctly and the differences we saw earlier were due to different default settings, not performance issue. Worthy is limited to NSGA-II as its only algorithm. In contrast, Tunny offers a wide selection of methods. For instance, using INGO, an advanced evolution strategy, Tunny converges to optimal solution significantly faster than Worthy. You can see the difference clearly. INGO reaches near optimal solution in roughly half the number of trials compared to the Worthy's NSGA-II. So let's wrap up the comparison with the key benefit of having multiple algorithm options. First, we verified that both two work correctly. When using the same setting, they produce comparable results. Tunny's flexibility shines with multiple algorithms optimized for different problem types. Advanced algorithms like INGO can converge significantly faster than traditional methods, saving you valuable time. However, there is an important trade-off. Choosing the right algorithm isn't always straightforward. In this sense, Ross's design philosophy is also valid. Providing one robust, reliable algorithm simplifies the user experience and ensure consistent result without requiring deep algorithm knowledge. Both approaches have merit depending on your needs and expertise. This is the final slide of the lecture part. I hope you've acquired the fundamental knowledge necessary to practical optimization. Start from the next slide. We will begin the hands-on session. But before we move to the hands-on session, let's take a 15 minutes break. Feel free to stretch, grab some water, and get ready for practical exercise. But before I start a hands-on session, please confirm the software requirements are always installed. Rhinoceros, Grasshopper, Git, and Tunny version 1.3.2. And please install Tunny environment to double-clicking Tunny Grasshopper icons. Okay, now it's almost 11 a.m. So 11:50 start hands-on sessions. Right, changing 11:50. Okay, thank you, Jim.
There's a question in the chat if there's a moment for a QA session, or if that could happen after the break, just regarding the lecture.
If you have any question for lecture part, please say in this time. Anyone have questions?
Hi, Jim. We're not
I can
hearing
hear
anything.
Jim.
Oh, hello. Can you hear me?
Yeah,
Yeah.
we're good.
So, I have a couple of questions. First one, thanks for the lectures. Very clear a lot of my thought. And my first question is, you have two slides specifically tells the decision making in between algorithms, the optimization method selection guide. I think that would be very helpful, but I wonder where those numbers came from. Any reference I can maybe study more about why you kind of branch out those decision making terms. That would be my first questions.
Yes. This is a very difficult question because the best optimization method is depend on what is your problem. Your problem, how many multimodal problem or very easy question. These algorithms have each characteristic. So please try and please check what algorithm have each characteristic. In the hands-on sessions, I make a time to try each optimization algorithm to understand each characteristic. So try to understand in the hands-on sessions.
Okay. I have my second questions are related to the first questions. Any reasons you kind of separated this into like two pages? One is without constraints, the other one with constraints. This constraints many makes a huge difference while we choosing different algorithms. Will this also be studied in the hands-on part? And I'm just very curious.
So also about constraints, I have some example for how to use these constraint optimization method and how to handle these constraints, each algorithms. So please join and please practice in my hands-on sessions.
Okay, thank you.
Okay, now it's time to try Tunny for yourself. Let's move to the hands-on session where you will get practical experience with the tool. First, get started with the basics of Tunny. We will walk through the fundamental steps so you can start using it effectively in your own project. Okay, we will start the simple addition problem to see how Tunny works. Please open the 01 addition file. I was updated this workshop material to Google Drive. I post the link to the comment. マテリア
I have the link right here. I can drop it in. It's also in the Slack.
Thank you, Nico. If you don't have the sample materials, please download this link. Okay, the opening the rhinoceros. And first, please type in the Tunny get license in Rhino command line to get Tunny license. If you get the license properly, the command line shows these keywords. The wake up, the grasshopper, and open 01 addition.gh. This is very basic setup, has two number slider for nickname A and B, and addition component, and the tiny fishing component. This component control optimization. And I recommend you to set nickname to the slider and the number component. Tunny recognize these nickname. So if you are already open this addition grasshopper component, please double click Tunny fishing component icon. And wake up Tunny UI. I talk about Tunny UI overview. At the top, you will find ribbon that allow you to toggle the display of various features such as optimization, visualize, output, and help. Go back to the optimize ribbon tab. When the UI first launches, it's default to the optimization mode interface. In optimization mode, the left section displays optimization setting, while the center section shows confirmation of objective function and variable configurations. By default, the system is configured to minimize the objective function. To maximize it, to instead select the max radio button in the objective settings section. The right section displays real-time optimization results when the optimization project exceeded. So let's walk through more detail about Tunny user interface. Starting with the ribbon and trial sections. At the top right, you can check whether you have obtained a license. If this section displays the community, you don't have one, please obtain one for 4 features. The ribbon shows all available sampling methods. Only sampling method available based on the number of objective function and the presence of constraints will be enabled. And this field, you will see the current selected samplers. In this case, I selected NSGA-II, and the Tunny default, the first setting optimization method is odd sampler. So maybe you can see sampler type is odd. The main panel of this field, input for determining both the number of trials and how long the optimization should run in seconds. And this study section, you can also configure a study setting. I introduced this field layer. And when you selecting the different samplers, like NSGA-II, the input change from number of trials to the number of generations and the population size, reflecting the specific requirement of genetic algorithm. This flexible interface ensures you have the right control for whichever optimization method you choose. So go back to the slide. First, let me explain what is a study is. Study is this group you can configure. Tunny optimization results are stored in this format. By default, the file named fish log on your desktop contains Tunny's optimization result output. Multiple optimization can be saved within a single file. Each individual optimization is called study. So in this example, Tunny log file includes study 1 and study 2 and study 3 and study 4. So include 4 study. Within a study, the actual optimization results are stored in each study. Each evaluation result is referred to as a trial. Trial contain variable value, objective function value, and attribute informations. The file itself is created in plain text format. As the optimization becomes slower with fish log file become larger, I recommend it create new file when appropriate, maybe 100 megabytes above. So go back to the Grasshopper. Let's look at how to manage result file. I called fish log file in Tunny. You can change the destination folder for result file from this folder icon, or click this button and save settings. No. Open result file configurations. So I clicked this folder icon. If you click the icon, this dialog will wake up. This variable shows the result storage field. When you can create new result file or opening existing one using the browse and new button, you can see the current path for both result file storage file and the artifact file structure directory. This is allow you to organize your optimization study and easily switch between different projects or experiments. For example, you want to create new study file and set any name you want. AECtech Tunny. So you set some file name and save. The result file storage path is changed. And click the save button to create new storage file. So I changed the storage file to the fish log and press save button. So back to the Tunny UI. The study field allow you to configure how optimization results are handled. In the Create New section, specify the name of the new study to be created. Since this is our first optimization, let's call it my first Tunny. And checking in memory improve optimization speed by preventing results from being saved to file during the intermediate stage. However, note the result won't be saved if Rhino crashes or encounter other issues. So use this option carefully. And the next item is continue checkbox. Continue checkbox allow you to restart existing study. You can select the study you wish to restart from the existing study box. So let's check the continue checkbox and check existing study box. Because we are doing no optimization, the box is empty. So unchecked. So when you are ready to begin optimization, please click Run Optimization button. But I recommend please use Auto Sampler for our first Tunny using step. So please check sampler type is Auto and the number of trials is 30. So if you set all configurations, let's start Tunny first optimization. So waiting some seconds, Tunny runs optimization and changing the slider value. And the real-time result is shown in the right side of Tunny UI. And by default, Auto Sampler has 10 random sampling. And after that, start to the optimization using the ZP optional. So please wait till the optimization is progress. So I set maximizing objective. So the result trial number 11 is achieved. Optimal value is 2. So maybe this optimization is already converged. If you want to stop the optimization, please click this stop button. Waiting and so the optimization is stopped. Tunny pop up this window. Solver completed successfully. So if you want to reinstate the optimal slider value, please click Yes button. And check the result. The number slider A and B both 1 and the objective value is 2. This is the optimal value of our additional optimization problem. So after optimization is completed, let's check the result. The odd sampler is extremely powerful. It may reach the optimal value of 2 before completing the set number of trials. So be sure to stop when it appropriate. In my case, the value reaches the maximum of 2 at 11th trial. This demonstrates the efficiency of the outsampler. It intelligently navigates the design space and can find optimal solution much faster than exhaustive research method. To view more detail about the results in Tunny UI, please select Output ribbon tab and click Selection. Ensure that the target study set to my first study and select all for group addition to display all trials in the listed trials. You can see the completed trial table of result with column showing ID, objective value, and their variables. And if you more this table query using output analysis tables, please set target to listed trials. Listed trials means this table. And please click generate. If you click the generate button, you can see the more clearly these trial results. And you can copy and paste these results to Excel or any spreadsheet applications. So if you want to reinstate the Grasshopper slider to the parameter value of a specific trial, simply enter the trial number in the Use Trial Number field and click Reinstate Slider. So probably, if you want to reinstate trial number 9, please set Use Trial Number field to 9 and press Reinstate Slider button. So Tunny shows this window and check the value is really reinstated. Now, trial number 9, parameter A is 0.15, and Grasshopper size, nickname A number slider's value is 0.15, and parameter B is 0.03, so B is also same value. So you can easily reinstate trial value to Grasshopper. For more detailed result analysis, use optional dashboard or Design Explorer. You can launch the optional dashboard by clicking optional dashboard button. The button is in Visualize tab and optional dashboard or TT Design Explorer. In this case, I use the optional dashboard. Please click this button to launch optional dashboard. If you click the optional dashboard button, the browser is wake up, and if the result don't appear immediately, it means the launch process is taking time. Please refresh. So please click try again or refresh. The dashboard needs a moment to load and connect your optimization data. This is a dashboard main screen displayed all your created studies. For example, let's select my first Tunny. When selected, you can view the details of the study. The dashboard provides various information graphs about study to help you understand the optimization process. On the first page, where you select the study, you can review historical data about how the objective function value changing during optimizations. And the hyperparameter information for optimization timeline and best value parameters and its value in the study artifacts. And go to the analytics page. There are many graphs, slice, encounter, and rank, and EDF. And trial list page, you can see all trial detail data. So go back to the top page of the study. One particularly useful feature is hyperparameter importance, which is visualize how much each variable affects the objective function. In our problem, we are optimizing A plus B, and both variables contribute equally to the objective function. This is what we'd expected mathematically. Since the function is simply A plus B, each variable should have equal importance. Examining the graph confirms these expectations. Variable A and variable B are both represented by raw chart showing nearly 0.5, B 0.54, and A 0.46. This clearly demonstrates that it contributes 0.5 to the objective function value. So if you want to get more accurately about the hyperparameter importance, please try to more trials. Because of few trials we do in case, the information is less. So the result is not equal to 0.5. So this feature becomes incredibly variable in more complex optimization problems, where you are not sure which parameter have the most impact. Hyperparameter importance helps you understand which design variable really matter, allowing you to focus your attention on the most influenced parameters. Okay, go back to the slide. This is a very simple problem of A plus B, but the number of trials required for convergence can vary dramatically depending on the optimization algorithm. So one example, I will try to use NSGA-II. So if you want to use NSGA-II, please click NSGA-II icon in Optimization tab. And please set number of generation to 10 and the population size is 25. And create new study name is my first GA. My first GA. And start the optimization. So waiting, the optimization is finished. Okay, the finished optimization. So the optimization convergence rate is very different from outsampler and NSGA-II. So I allocated about 15 minutes of time. Please experiment with how different methods affect convergence using your Grasshopper environment. Since this is single objective optimization, you can test 30 different methods to facilitate comparison later via the dashboard. It's good practice to name your study after its method. For example, TP addition or NSGA-II additions. You can see all available methods in the label. Outsampler, TP, GP optional, GP voltage, HEVO, NSGA-II, and 3, CMA-ES, and DE, Ingo, rundown, QMC, and brute force. This hands-on comparison will give you practical insight into how algorithm choose affect optimization efficiency. So before start exercise part, I introduce how to use optional dashboard compare features. So reopen the optional dashboard and go to optional dashboard top page. So clicking this home icon is go back to the first top page of optional dashboard. On the top right corner of the dashboard main page, you will find the compare button. Clicking this button will take you to the comparison page. Holding down the shift key while clicking study name, on the left side, you can include multiple results in the single graph. This makes it easy to compare convergence patterns side by side. In the example shows, I am comparing my first study using outsampler and my first GA using NSGA-II. The history plot on the right display, both optimization run override, allowing you to clearly see which method converges faster and more efficiently. This comparison feature is invaluable for understanding which algorithm work best for your specific type of problems. So reiterate, even an extremely simple program like A plus B can vary significantly depend on the optimization method. Please experiment with different approaches yourself to truly appreciate the need for multiple methods. Keep in mind that the most appropriate method varies by problem. So these results aren't necessarily applicable to all cases. What works best for this simple addition problem might not be optimal for your complex structure or architectural design challenges. Take about 15 minutes to optimize your own and experiment with how different approach affect each method. Try several algorithms or several algorithm settings. Compare their convergence pattern in the dashboard and see which one finds the optimal solution fastest. This hands-on experience will build your intuition about algorithm selection knowledge you will apply to real design problems. So let's start the practice time. So let's do your environment. Or if you have any problem to running Tunny, please comment and chat or say. And I set the time. Now is 11:47. So practice time is end. Just 12. Let's start practice time.
Playing around a little bit, I came across the warning about using Python nodes within your script. Would you be able to speak a little bit to that and what to like look out for in relationship to tuning?
Please post the error message to the chat.
Okay, it's more like a warning. It says like, I'll try to post it, but it says, you know, Tunny noticed there's a Python script component suggested to use C#, something to that effect.
So if you have any problem to installing Python code, Tunny has a reinstalled Python library button. So please try to reinstall Python library related Tunny environment.
This was specifically about like in your Grasshopper script. I think if you had created like a script instance in your script with a little bit of custom code. I'll see if I can. I'll share.
You mean using Python 3 components in Grasshopper? Yeah. I see. I understand this problem. In the Python 3 component and the Tunny using the same library. So Python 3 using Python.NET and the Tunny also using Python.NET. So maybe the version of using this component is conflicting. So I want to fix this problem, but I can't find which version the Lino, the Macroneil using this Python 3 script. So I use Python 3 script very many times. So I want to fix this problem.
Yeah, I've used the Python script a lot, but I've also had a lot of problems with it in Rhino 8 and Rhino 8.
Hello. I have one question regarding to the generative algorithms showing on the dashboard. So Tunny use trials for, I don't know if it's equals to generations concepts in the GA, but from my understanding, each generation should have some certain amount of population size. So I'm wondering if these trials equivalent to the generations, and also if it's so, which one was selected to represent the generation, because like each generations will have certain amount of populations. So I'm curious about the like how's this things being selected and shown, if it makes sense.
Yes, and if you set the number of generation is 10 and the population size is 25, the first generation is all of them is make parents. And the next generation, there are 50 trials, 50 individuals. In Tunny algorithm, choose best 25 trials, make it parents, and cross over each parent to make the offspring. And choosing the parents is randomly. Is this answer for your question?
My question is more about if now on my settings, numbers of generations 15 and populations size is 3, then
3.
I will have 45 trials now, but I don't know which trials belongs to which generation. It's just like 0, 1, 2 trials from the first generation and 3, 4, 5 from the second generations. Is that so?
So every generation decide the best trial make parents. So if you choose a population size is 3, each generation get the most best 3 population make the parent, and make next generation, these 3 parents make 3 offspring and compare the before generation and this generation trial value, and the best 3 population make the next generation parent.
Oh, yeah. Yes, I think I understand it, the NSGA roughly, but I'm more, I was focusing more about on the Tunny dashboard, because now each trials are separately, so each child behaves like a population solutions. So we didn't know which solutions come from which generations.
Sorry, I don't understand your question clearly. So maybe we will talk about this topic later or in New York.
Yeah. Thank you.
Thank you. Sorry. And I will answer the question in the chat field. The first one is it possible to export the data as a CSV without copy pasting from the selection tab? The answer is yes. The next practice session, I talk about more efficient way to export the trial data to CSV. And next question, for NSGA-II, is there a rule of thumb about number of generation and population size based on number of parameter or objectives? I don't have any solid answer, but I usually set population size is 50 and generation size is 24 or 50. This is my first step setting. And the next question is, does Tunny show which optimization method is used when the autosampler is selected? This is good questions. You can see what method is used in autosampler in the Tunny result file. So please check the Tunny result file, the fish log file, and double click and open the result file. This is a Tunny result format. Tunny saving the result file in plain text. And each code is one operations. The first code means my first Tunny direction is 2. 2 means maximize. And the variable name is A and B. Using Tunny version is 1.3.3, blah, 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 blah. And this is very important line. Trial ID 0 is first trial. Is autosampler colon random sampler. This means trial ID 0 is using random sampler. And trial 1, autosampler, ZP sampler. So you can understand trial ID 1 is using ZP sampler. ZP sampler means tiny optional. ZP optional. So you can see what sampler is using. Okay, any other questions? If you don't have any questions, we go to the next sessions. I'll go back to the slide. Next, I will introduce tiny attributes and artifact feature, as well as how to build them in dashboard. So let's explore some of tiny distinctive features, constraints, attribute, and artifact. Please open the file name 02attr and altf.gh. This file contains is extremely simple. It displays Rhino logo with size method, size modified factor. So the scale factor is large, Rhino icon also larger. This is a very simple optimization setting. The variable is Rhino logo scale factor, and the objective is the logo volumes. And the next, I will talk about Tunny's ATTR's input. ATTR's means attribute. So now introducing the construct fish attribute component that adds attribute information to trial. And this file contains a constraint setting. Constraint can be configured using this constraint fish attribution component. Tunny constraints are implemented as soft constraints. More detail will be provided later. And C constraint input. The constraint conditions for Tunny are evaluated based on input to constraint. If the input here is 0 or less, the trial is judged as a feasible solution that satisfies the constraint conditions. The input of constraint can be erased, and evaluation is performed for all values entered. For value rather than 0 or rather the value, the more the trial is judged as following to satisfy the constraint conditions. Fish attribute, as the name suggests, attaches various information to optimization trials. Not just constraint, but any type of data can be handled. For instance, here we are storing simple scale information under the info field. These components support Zoom interaction, Zoom user interface interaction, allowing you to increase input value when approaching the interface. So you can add many attributes or you can delete. Attributes are stored as key value pairs. The key represents the name of component input. So info nickname make the key, while the value is actual input value. So key is info and the value is Rhino logo scale 0.46. And the next new item is Tunny ARTF's input. This is artifacts input. So item displayed in red represent artifact input, while similar to attribute, in that they provide additional information for trials. These store files rather than numerical value over strings. You can also directly import geometry or save model displayed in viewport. Fish point by capture is a component that creates an artifact from the currently active viewport as an image. So before start optimization, I talk about what is soft constraint. Go back to the slide. Soft constraint is a very important concept in Tunny. Tunny is that constraints are implemented as soft constraint rather than hard constraint. This means solutions that violate your constraint can still appear during the optimization process. If you are new to optimization, this might look like something is wrong with your setting. But this is completely intentional. Why soft constraints? The optimizer runs from constraint violation to understand where the boundaries of feasible region are. By exploring infeasible solution, the algorithm can find better feasible solution nearby. So don't be alerted if you see constraint violation during optimization. The algorithm is actively running, and over time, it will converge toward constrained satisfied solution. So in this session, we'll go through some key features you will use during hands-on practice. Dashboard basic and attribute and artifact handling. So go back to the Grasshopper and waking up Tiny UI. And let's start optimization. Maybe in this case, this problem is very easy. Set the generation is 10 and the population size is 25. The study name is ADT. Attribute artifact. And start the optimization. Tiny no response. Sorry, Tiny, my Tiny is no response, so I will start Buenos Aires. So we open Rhino. We get Tiny license. Waking up Grasshopper. Now open artifact file. Beside the liner window. Looking at Tiny UI and start. ATTRs and ARTFs. Generation is 10 and population is 25. The Tiny default setting will optimize. Okay. Tiny running correctly. Waiting, the optimization is finished. So in this case, number of generation is 10 and population size is 25. So Tunny tried 250 trials. Okay, I stop this optimization because of time consuming. Yes. Okay, if you stop or end your artifacts and attributes study, please open optional dashboard. So, and open artifacts and attributes study. So let me explain some important dashboard basics. Many plots with gray color represented infeasible solutions that do not satisfy the constraint. There are solutions that violate your design constraint during optimization. Remember our discussion about soft constraint earlier. In this case, many of plots are infeasible trial. So I want to change the history plot scale. If you want to change global scale, please enable to this log Y scale toggle. If you enable this toggle, the y-axis is changed to using log Y scale. So the dashboard is highly interactive. All charts can be manipulated using mouse, making interpolation intuitive and fluid. For instance, with history plot, you can adjust the display range using log scale toggle and input directory. So by double clicking on axis endpoint, and set some number, in this case, I set 10. The upper range is changed to 10. So if you want to go back to the default window, please double click. Double click the plot area or press this reset axis button. And adjust display range by dragging and dropping on the mouse to zoom into specific regions. And click any point of interest to jump to its detailed view, where you can see in the parameter value and other trial information. So like this. So I talk about this page called trial detail page appear when you click on any data point or selected a trial from the list. So you can view information not only click on plot points, but also by pressing this trial list button. This display shows all relevant information about the trial, including parameters and objective value and attributes and artifact. In attribution section, display the value set for the fish attribute in Grasshopper. These are custom data you can track for each trial, like structure, ratio, cost, or any other metric you want to monitor. In this case, we set attribute, constraint, and info. So go back to the option dashboard. You can see constraint and info, both attribute value. And the artifacts section can display various file formats. In addition to image, when you input brep or mesh into artifact, you can view and manipulate on the 3D object view, but there are no items. So maybe some bugs in this version I will fix in next release, but Tunny running correctly, you can see your Rhino 3D model very interactively in browser. And you can also associate any file, such as CSV file, with analysis result, making it easy to track all data related to each optimization trial. So if you want to attach the CSV file, Tunny supports directory file path input. So pass to your CSV file. Set the text in the you want to attach the artifact and directory input artifacts. And I will introduce about smart selection, which supported selecting trial option. On the top of the page, you will find these three options. The first option is whether the restrict selection to only feasible solution that satisfy all constraints. This is useful when you want to focus only on valid design options and exclude any constrained violated solutions. The second option is whether to display dominated individuals during multi-objective optimization. In multi-objective problems, dominated solutions are those that are strictly worse than other in all objectives. Hiding them can help you focus on the right optimal solution. And third one is whether to display artifacts. Registered through the artifact feature mentioned earlier, this is particularly useful when working with 3D model or any images. You can quickly filter to show only trials that have associated geometric or visual data. These filtering options help you navigate large optimization study efficiently. So in this case, make false to this first option. On the parallel coordinate plot, you can filter which trial to display on the page. Selection can be made by dragging along the axis. Simply click and drag on any axis in the power coordinate plot to create selection range. And if you double click this range, the selection is deleted. So in history, for example, selected trial appear as color point, while unselected trial appear as unfilled circle. This visual distinction makes it easy to see which trial match your filtering criteria across all the visualization. This interactive filtering is incredibly powerful. You can quickly isolate trial with specific parameter range or performance characteristics, then examine them in detail across all the dashboard view. So when artifact enabled, you can display a list of artifacts at the bottom of the page. So the 3D model view has some bugs, so change the artifact number 1. Only selected items are displayed. The artifacts shown correspond to the trial you filtered using the parallel coordinate or other selection method. In border color indicates the degree of objective function evaluation. Darker color represents better objective function value. For minimization problem, this means smaller value. This color coding makes it easy to visualize, identify the best performing design at a glance. When there are multiple artifacts or objective function, you can select which one to choose from the drop-down list. This feature is particularly powerful for design problems. You can quickly browse through dozens or hundreds of design variables stored by performance and visualize, compare them side by side. And at the bottom of this page, you will find table containing detailed information about your selected trial. Here you can view all detailed values, parameters, objective, user attributes, constraint, and any other data associated with the selected trial. If you would like to perform more in-depth processing, you can download this table CSV format. This is particularly useful for further analysis in Excel or other spreadsheet, statistics processing in Python or R, creating custom visualization, sharing results with team member. To download it, please click Download CSV file button at the bottom left, the table. The CSV will contain all the information for your filtered selections. So if you want to download all trial data, so set include visual trials and double click reset to your filtering. And disable show artifact. You can see all trials in this table, and you can download all these data to the CSV file. So while dashboard is very extremely useful tool, do you assume you can only open it through the Tunny UI? You can actually launch it from Grasshopper UI as well. Let's examine the functions available in the the toolbar at the top of Grasshopper interface. Here you can access help documentation on the tutorial files of Tunny and the opening optional dashboard and the TT Design Explorer. So you can quickly access to all key features or Tunny key feature without needing to navigate through the component interface. And when you are just looking to review results, constantly waiting for Grasshopper to launch can be somewhat tedious. Tunny allows you to launch the dashboard in Rhino by executing the Tunny run dashboard command. This command eliminating the need to launch Grasshopper itself. So this is particularly useful when reviewing results from previous optimization runs, showing results with colleagues who don't need to edit the definitions, and quick comparison between different studies. And the next topic is LLM support result analysis. This feature is one of the most exciting features is that Tunny supported optional dashboard LLM integration, which means you can analyze your optimization results using natural language. Instead of manually filtering data or writing queries, you can simply ask questions in plain English. The LLM integration provides intelligent data filtering and interactive analysis, helping you extract meaningful insight from your organization and without needing to write complex any code. This brings AI-assisted analysis directly to your design optimization workflow, making the entire process more intuitive and powerful. So this is a home for configuring the storage location for result. After introducing study, on the right side of this form, you will find setting for integrating with LLM setting. Enter the desired LLM model and its API key and API URL. Then launch the optional dashboard to enable the LLM integration functionality. This highlighted section shows use LLM checkbox. It is neat to enable using tiny LLM features. For more detail about this feature, please refer to the documentation page for optional dashboard. So it is neat to use OpenAI compatible API service to use this LLM feature. If you're interested in trying this LLM integration feature, I recommend it to use the Grok service. This is Grok homepage. While OpenAI's API services are paid, Grok currently offers a fully compatible service for free. You can easily start testing this LLM integration by simply registering an account and obtaining an API key. Grok is very fast and provided response at a very affordable price, making it perfect for getting started. When using Grok, I recommend it to use OpenAI GPT-OS's 120 billion model or a model with higher performance model. Models with lower capability often make analysis error, so it's worth using a more capable model for reliable results. So I will do demo. I am already break tiny optional dashboard using enable to the optional dashboard LMM integration option. So I open the CMA-ES result. This is this study history. And go to smart selection page. If you enabled LM feature, this query field is appeared. So for example, input trial, no, result smaller than 1, and quick filter button. So the LMM make a filter function. So like this, and you can check this function is safety, and there is no problem. Please push allow this function button, and then you can see the probability coordinate plot upper range is below 1. So the LMM feature, LMM considering this natural language query and reflect the filter to probability coordinate or any other smart trial selection pages items. And next feature is in analytics page. Go to the bottom of this page. There are graphs generated by LLM. So you can also input this field to any natural language query to generate any plot. So for example, input the plot objective value versus trial number and generate. Of this function, you can see the LLM generated graph of the first objective versus trial number. And the other example, so the pie chart group the objective function value into 10% interval and plot them to show how each interval contains different number of individuals. So the query is making the pie chart and press generate button and waiting and press allow this function. You can see the LLM generated pie chart. In this case, many trials in 90 to 100%. So you can analyze these optimization result using the LLM feature. So the next topic is let's explore how different objective and algorithm perform with Tunny. We will use benchmark function to compare algorithm performance and understand how the number of objectives affect optimization behavior. This hands-on exploration will help you choose this right approach for your own project. So I want to try yourself how objective and algorithm differ. So in earlier addition example, auto sampler and GP optional converged very quickly, where it performed as well on this more challenging problem. For advanced user, please try and multi-objective optimization, ZDT1 function, to see how different algorithm handling multiple objective. So at first, I will introduce these benchmark function in the following slide. So don't worry, you are not familiar with them yet. The Oakley function is widely used benchmark in optimization researches. It is designed to test how well optimization algorithms can handle the complex multimodal landscapes, meaning it has many local minima that can trap poor algorithm. As you can see from the visualization, the function has a highly large surface with numerous peaks and valleys. The global optima is at 0.0, marked by the raster on the counterpart, where the function value reached in minimum. This challenging landscape makes it an excellent test case for evaluating optimization performance. If an algorithm can efficiently find the global optimization here, it demonstrates robustness in handling real-world design problems with similar complexity. And the ZDT1 function is a classic multi-objective optimization benchmark, unlike single-objective problems. This function has two competing objectives that need to be balanced. The left plot shows the objective space with random samples scattered throughout. The red curve represents the true part front. Part front means the set of optimal trade-off solution where you can improve one objective without worsening the other. The right plot showing the zoomed view of the part front clearly illustrating the smooth trade-off curve between the two objectives. This benchmark is ideal for the testing multi-objective optimization algorithm and understanding how they explore and converge toward the parade optimization solutions. And in this slide, I talk about why does ZP. ZP means ZP optional and the autosampler struggle with the Oakley functions. The key is the complexity of the landscape. For the addition problem shown on the left, the function is smoothly and simple, easy to build an accurate surrogate model that predicts the function behavior. However, Oakley function shows on the right, has a highly irregular multimodal landscape. This makes it too complex for surrogate model to capture accurately. The GP surrogate it can build a reliable model of such a large surface. This demonstrates an important lesson. No single algorithm is best for all problems. The effectiveness of an algorithm depends heavily on the characteristic of your landscape of optimization. So now it's time to apply what you learn and perform optimization yourself. Try answering these questions. Which sampler performs best for optimization? Remember, the number of objective function also affects result. So experience it for yourself. If you want to experiment with other benchmark function or review the decision flow for selecting sampler we demonstrated earlier, you can check the Tunny documentation website. This link is provided to the benchmark function in Tiny Docs. So I already distributed this slide PDF file. If you want to go to the benchmark function detail or optimization method decision tree, please click the benchmark function link. And let's start to the practice time to the trying to optimize benchmark functions. I talk about how to use benchmark functions. The benchmark function is located the left side of Tunny bar. There are some benchmark functions. If you want to try Oakley function, drag and drop Oakley function, if you set the Oakley function, there is automatically set the variable using the GNF rule. The value range is a recommended range to optimize. Set the tiny fishing component to connect variable input to the GNF rule and the objective to the Oakley objective output. If you want to try multi-objective optimization benchmark function, please choose these 4 benchmark functions. So for example, ZDT1 variable is like this. Connected variables to the GNF rule and objectives is connected to objective 1 and objective 2. Okay, let's start practice time. Let's try to optimize these benchmark function yourself. Okay, the exercise time is over. So I apologize for not managing my time well. Since we've reached the end of our workshop time, there are still slides remaining, but I'd like to conclude with this slide. Tunny still has many more features. Please try them out. So the last slide topic is in actual architectural design problem, which approach would be most effective? Let me introduce a research paper as an example. This research used both opossum and Tunny for analysis and focused on the facade design and environmental performance of office building. The diagrams show how different elements, shading window, and facade components are parametrically controlled. And here is the key findings. Since environmental analysis of facade requires significant computational time for each evaluation, this paper recommends using SMBO-based method like TPE or RBF-opt as appropriate approach. This is exactly the kind of algorithm selection guidance we discussed earlier. Matching the method to your problem characteristic. This demonstrates how Tunny is being used in real architecture research to solve complex multi-objective building performance problems. For detailed information, please refer the original paper. the optimization and expensive multi-objective building performance problem. Benchmarking model-based optimization algorithm against meta-heuristic with and without surrogates. So go to the last slide. Tiny have human in the loop feature and the exploration of design space. But skip. So this is our final slide. Thank you for joining today's Tiny lecture and hands-on. We've covered a lot of ground, the understanding optimization algorithm and the benchmark function to hands-on practice. Even exploring advanced features like LLM-based analysis. I hope this workshop has given you the knowledge and the confidence to apply Tunny to your own design challenges. Whether you are optimizing structure performance, exploring design space, or incorporating human preference, Tunny is here to make your parametric design process more powerful and efficient. If this workshop has been helpful to you, I'd be right. Happy optimizing, and thank you again. Thank you.
Thank you so much. It was a great workshop. And